describe transformations of exponential functions. So remember that the function f of x equals e to the x is the parent function of the family of exponential functions. E is a special number, which is Euler's number, and it's one of those numbers like pi that we use in math. So when we talk about transformations of exponential functions, we want to think about functions in groups. Okay, so those groups are like subfamilies that contain functions that all have the same base. So for example, if we consider all the functions that have a base of 2, we can use f of x equals 2 to the x as like our parent function. Okay, so then we can think about this question like what happens when f of x equals 2 to the x is transformed to g of x equals 2 to the x minus 4. Well, the minus 4 is outside the exponent, right? So it's going to affect the output. So that is going to shift the function down 4 units. So when we talk about transformations, remember there are 3 types of transformations. We can have shifts, which are translations, left or right, or up or down. And then we can have stretches or compressions, and we can have reflections. So when I'm describing this equation and just telling you where to look for A, B, H, and K, I'm going to consider the subfamily that has a parent of y equals 2 to the x. Okay, so I'm just using that for a reference. Remember, if you're looking at a different group of functions, you can change the value of this base, and then the parent function will be different. Okay, so if 2 to the x is the parent function, if I put a number a in front, okay, that is going to be a vertical stretch if a is bigger than 1, and a vertical compression if a is less than 1. It's going to be a reflection over the x-axis if a is less than 0. If I change something within the exponent, it's going to be like having a change within a radical. Okay, so this is like the inside part of the function, the exponent. So if I have b, that is going to be a horizontal stretch if b is less than 1, horizontal compression if b is bigger than 1. It's going to be a reflection over the y-axis if b is less than 0. If we have an h, okay, h is also going to be inside the exponent, so it's going to go left if h is less than 0, which will give you a plus sign in the problem. Going to go right if h is bigger than 0, which gives you a minus sign in the problem. If we have a k on the end, okay, that's outside the exponent, so it's going to go up when k is positive and down when k is negative. So that set of equations is in your study guide along with this flowchart. Remember, you can use the equation or the flowchart, whatever you need in the study guide to help you answer these questions. So let's describe the transformation that takes function f to function g. We have f of x equals 2 to the x and g of x equals 2 to the x minus 5. So kind of the change that's going on here is this minus 5, right? So that's the new part. So let's think about what's going on. So it is outside the exponent, so it's going to be a vertical change. It's being added or subtracted, and that k is less than 0. Okay, so it's going to be a shift down 5 units. Now let's try this problem. So we have f of x equals 2 to the x, so that's our parent function, and then we have g of x equals 3 times 2 to the x. So notice that we have this value of a, which is 3. That's on the outside, so it's going to be a vertical change. It's multiplying the function, and that value is bigger than 1. Okay, so that 3 is going to create a vertical stretch. Okay, notice that we're always comparing it to that parent function that has the same base as the function that we're talking about. So now let's compare 3 to the x and g of x equals 1/3 to the x. Well, you may be looking at this problem and saying, wait, hold on. These two functions don't have the same base, right? Because we were saying we could compare functions that have the same base value. Well, but remember, we also know how to manipulate functions so that they can have the same base. So for example, like maybe I can turn this 1/3 into a base of 3. Okay, if you remember the exponent properties, remember that I can rewrite this as g of x equals 3 to the negative 1, right? Because 1/3 is the reciprocal of 3, so I can write this as 3 to the negative 1 to the x. Okay, so when I rewrite that, that's going to be like g of x equals 3 to the negative 1x. Okay, so you can see now this is basically a transformation when I've added in a value of b, right? So I have a number right here. Okay, so it's inside my exponent, so that's going to be a horizontal change. It's multiplying my function, and it's not a stretch or a compression. Okay, so for a stretch or a compression, it has to be less than 1 or greater than 1, but not equal to 1. However, it is less than 0, okay, so I'm going to have a reflection over the y-axis. So that -1 is going to have that effect that it's going to reflect this graph over the y-axis. And actually, remember, you can always check your transformations by going to Desmos. So let's just verify that what we found is true by going to Desmos and graphing both of these functions. So let's graph 3 to the x, and let's also graph 1/3 to the x. Okay, so let's graph both of these as they were originally written in the problem. And you can see that when I zoom out, you can see that what we do have is a reflection over the y-axis, okay? You can see that the original function in purple is 3 to the x, so it goes like this. And then the 1/3 of the x is in black, so it goes like that. If you can't see it with the grid lines, remember you can click settings and then change the color. So you can see now in blue, we have that new transformed function, okay? So you see what it's done is it's taken it and it's reflected over the y-axis. So anytime you're doing a transformations question and you're just kind of in doubt whether your answer is correct, remember you can always use Desmos to verify your answer. So now let's try describing the transformation that takes f to g when we have f of x equals e to the x and then g of x equals e to the x minus 5. So once again, e to the x is our parent function, and notice that the new thing we have is this minus 5 on the end, okay? The minus 5 is on the outside, so it's a vertical change. It's being added or subtracted, and it is going to be a shift down because that is less than 0. Okay, so it's going to take this graph down 5 units. So we can also remember verify this using Desmos. So let's go ahead and do that. So we have e to the x, and then we have e to the x, and then click out of the exponent because that minus 5 is on the outside. Okay, and you can see what it's done is it's shifted the graph down 5 units. Right, it originally had a y-intercept of 1, and then now it has a y-intercept of -4. So let's also now describe the domain, range, and asymptote of g. Remember, we can do this without looking at the graph. So let's go ahead and describe it, and then we can verify with what we have on the graph. So remember, we know that the domain, because it's an exponential function, we know the domain is going to include all real numbers. Okay, so it's going to go from -infinity to +infinity. So to describe the range, remember, we need to know the asymptote. Well, remember that minus 5 is our value of k, so that's going to tell us that we have an asymptote at y equals -5, right? So that's going to be my horizontal asymptote. So now remember, since e to the x is positive, right? So like here, a is basically 1, which is positive. My range is going to be all y values greater than -5. So I would say that it's going to go from -5 to +infinity. Well, let's go to the graph and verify that this is in fact true. So the domain, you can see here, it does in fact include all real numbers. So the domain is going to go from -infinity to infinity, okay? Notice that the range, we do have that asymptote here at y equals -5. And then it goes above y equals -5, right? So it's going to go from -5 to +infinity, which is exactly what we predicted by looking at the equations. Okay, so you can figure out domain, range, and asymptotes from the equations, or you can do it by looking at the graph. So I just want to make a quick note about reflections. So when we're transforming a function that's in the form y equals a b to the x, okay, so like when we had the y equals 2 to the x, if you add in a value of a that's less than 0, it's going to reflect it over the x-axis. However, if you have a function that's in the form y equals a b to the x plus k, just making a negative is actually going to reflect it over the asymptote. Okay, so what's different here is like this function has an asymptote of y equals 0. This function, since it has the plus k, will have an asymptote of y equals k. So if you only make a less than 0, it's going to reflect it over the asymptote. To reflect it over the x-axis, you have to make the entire function negative. Okay, so what you have to do is you have to take a b to the x plus k and make it y equals -ab to the x minus k. Okay, so that's going to reflect over the x-axis, but if you make just a negative, if you have y equals -ab to the x plus k, that is going to go over the horizontal asymptote. Okay, so let's look at an example. So identify the functions that represent the reflections of the graph f of x equals negative 1/3 to the 2x, negative 1/3 times 2 to the x plus 2 over the x-axis and over the line y equals 2. Okay, so what's significant about y equals 2? Notice that it's the value of k, so that is our horizontal asymptote. Okay, so remember what we said on the previous slide was that to reflect it over the x-axis, we have to make everything negative. Okay, so we're going to take f of x equals negative 1/3, 2 to the x, plus 2, and then we actually, what this is called is it's called saying negative f of x. Okay, because what you're doing is you're taking the whole function and you're just multiplying the whole entire thing by negative 1. So when you do that, you're actually going to distribute that negative to both terms. So this is going to become negative 1/3 is going to become positive 1/3. So we have 1/3, 2 to the x, and then negative of plus 2 is going to be minus 2. Okay, so I'm predicting that if I have a function, let's say g of x equals 1/3 times 2 to the x minus 2, that's going to be reflected over the x-axis. So let's go to Desmos and make sure that that is in fact what happens. So I'm going to type in the original function. So I have negative 1/3 and then times 2 to the x. Oops. And then plus 2. Okay, so there's my original function. You can see it has that horizontal asymptote at y equals 2. And now let's type in that function that I made everything negative. So I have 1/3 times 2 to the x and then minus 2. And you can see that it is in fact reflected over the x-axis. Okay, so making both parts of that function negative reflected it over the x-axis. Well, now it wants us to reflect over y equals 2. Okay, well, remember what it said is that just making a the opposite sign is going to reflect it over y equals 2. So what I'm going to do is I'm going to change that negative 1/3. I'm going to make that a positive 1/3. Okay, so I have a new function, h of x, and I'm going to make that positive 1/3 times 2 to the x, but then I'm going to leave that plus 2 the same. Okay, so let's see if that does in fact reflect over y equals 2. So I'm going to clear this out, and then now I'm going to enter this function 1/3 times 2 to the x, and then I have plus 2, and you can see it is reflected over y equals 2. Okay, so you see how the black function and green function are reflections, but it's reflected over y equals 2. So now let's just go back to these kind of questions. Let's describe the transformations from f to g. Okay, so you see what's different between f and g. Notice that neither of these is like the parent function, right? So this is already a transformed function, and then it just changes the transformed value. So originally we had 3 times 2 to the x, and then what they did is they changed that 3 to a 4, okay? So what will actually happen is like this graph is already vertically stretched, right? But this is vertically stretched by 3. Right? Because we have a number that's on the outside, it's a vertical change, it's being multiplied, and it's bigger than 1. So this is vertically stretched by 3, but then this is going to be vertically stretched by 4. Okay, so if you think about it, if you're stretching something by a factor of 4 versus stretching something by a factor of 3, it's going to be more vertically stretched. Okay, so sometimes you can already transform a function that's been transformed. So it's just going to become more or less of the change that's already occurred. And once again, if you want to verify, just go to Desmos and type in both equations. So if we look at 3 times 2 to the x, and then we compare it to 4 times 2 to the x, notice that the blue graph is more vertically stretched, right? So if we zoom in, you can see how it's like going a little bit more quickly up in the vertical direction. Function g is formed by vertically translating function f. Write the equation of function g, and it tells us that f of x equals negative 2 times 2 to the x minus 1. Okay, so what we're going to do is we want to do a vertical translation. Okay, so remember from back when we talked about the equation, remember that to vertically translate something, right, we're moving it up or down, so we need to change the value of k. Okay, so we want to think about how k is being affected between function f and function g. Well, what happened? Okay, so did it go up or down? We'll notice that from f to g, our function went up, and then we just have to count how many units. Okay, so it went up 1, 2, 3, 4, 5. Okay, so it went up 5 units. So what it's going to do is it's going to change this value of k. So what we're going to do is we're going to add 5. So that means that g of x is going to become 2 times 2 to the x, and then minus 1 plus 5 is going to become plus 4. Okay, so that's how you write the equation of a function. So notice that it's already been transformed, but we just performed an additional transformation on it. So by looking at the equation of an exponential function, you can determine the transformations depending on how the values of a, b, h, and k are changed. Remember to group functions into subfamilies to compare and study transformations.